This presentation is about multiple MIPI CSI-2 cameras leveraging FPGAs, and is done by an old friend of mine, Ted Marena. Ted is a director of SoC FPGA marketing at Microsemi. He has over 20 years experience in FPGAs, and he was awarded Innovator of the Year award in 2014 while he was working at Lattice Semiconductor. Marena has defined, created, and executed unique marketing platform solutions for vertical markets, including consumer, wireless small cells, industrial cameras, displays, and automotive applications. Ted started working as a design engineer, field application engineer, and a sales manager before moving to marketing. His understanding of the complete electronics design cycle has earned him a reputation of an expert in the semiconductor industry. Ted holds a Bachelor of Science in Electrical Engineering, magna cum laude from University of Connecticut, and an MBA from Bentley College. Please welcome Ted.
Thanks, Satwan. Appreciate the intro.
Come on. Should be good to go.
Okay, this is the clicker? That's it. Okay, great. Thanks so much. I really appreciate it. So as Satwan had mentioned, we worked together previously, and it's really nice to see him and some of my other former colleagues. So I'm the director of SoC FPGA marketing at Microsemi, and when I submitted to put this paper together, I really thought it was a perfect time to explain to everybody and educate folks on where FPGAs are continuing to be used with cameras, more specifically CSI-2 cameras. So let's take a look at the agenda and what I really wanted to walk through for everybody. And some folks are very technical, and you may be extremely familiar with CSI-2, the interface and what it is. Others may not be that familiar with it. So what I really wanted to do was spend a few slides on the interface itself. And I think that that's important because a lot of people may not understand how FPGAs are interfacing to CSI-2. So I'll take a little bit of time and explain that. And then I'll give a high-level overview of where FPGAs are typically used in leveraging CSI-2 interfaces. Then we'll get into really the meat of the presentation, and I have a lot of design examples where I'll show and explain how FPGAs are used in multi-CSI-2 camera applications. So there's a lot of use cases for these, a lot of different markets, and that's what the presentation will go through. So hopefully by the end you get a good idea and an overview of the high level on the standard, how FPGAs interface, and some of the areas that they can be used and are being used. Okay, so I want to rewind a bit for those of you who may not know the history of image sensors. For a long period of time, the common interface was a parallel interface. And so this CMOS parallel interface, just trying to see if I can get the pointer here. Okay, great. So this CMOS interface worked for a number of years, up until the time when the megapixels became to around 2 to 3 megapixels. In that sort of range, and of course it depends on the frame rate, the CMOS interface had to run faster and faster, and it started to affect the quality of the sensor. So a lot of vendors moved to some very interesting differential but proprietary standards. Aptina, which is now on Semi, had introduced HiSPI, and folks like Panasonic and Sony used a sub-LVDS type of interface. And as a matter of fact, these interfaces to some extent in some markets are still used. But largely what's happened is that folks have migrated, and there's obviously a reason why people have migrated. And that reason really comes down to the fact that the CSI-2 standard was used in mobile. And a lot of people are familiar, and I'm sure you know, a few years back, the mobile interface really became the dominant architecture. Now, this is kind of the system diagram from the MIPI webpage. I just was looking, it's just honing in on the fact that even though the physical interface, the DPHY, is used for displays and cameras, this is just focused obviously on the camera side. Okay, so I like to, again, just get everybody baselined and understanding where we are and how we got here. So a generation ago, designers looked at the personal computer and said, this is excellent. It's high volume architecture, the components are very reliable, they're very inexpensive, and no matter what I'm making, if I can use a part that's targeted for a PC, I'm gonna get great cost, good power profile, reliability. And so everything started to adopt that platform technology. Well, in 2012, when the smartphone outshipped the PC for the first time, and today it's multiplied how many more mobile products are shipped than PCs. Designers today, and for the last couple of years, have really now started to say, hey, how can I use products for mobile architecture in my design? So maybe you have a medical product that needs a camera. There's lots of applications for cameras and displays in medical applications, industrial, inventory management, machine vision. It goes on and on and on. And so just like a decade ago when the PC architecture found its way into the embedded and the broad market, the same thing is happening where people are going to utilize components from the mobile architecture for the broad market. And this is why CSI-2 has really become quite a dominant standard. Okay, so that was my history lesson for today. Hopefully you enjoyed that. Now, I wanted to step into some of the technical side of it a little bit. When I first learned about this standard, I started reading about it, and I was really quite confused because I said to myself, why on God's earth do we need to have this high-speed signaling, and then on the fly, each leg of the high speed needs to transition to this 1.2 volt CMOS interface? And I thought to myself, there must be a reason why. I don't know what it is. Whoever originally created it probably had a lot of good reasons to do this. Obviously, there's a number of IP cores that are available that are dropped into designs that do this. But from someone who came from an FPGA and a digital logic background, I kind of looked at this and it was very puzzling. But be that as it may, there was something that we figured out, which was that you could detect when you were going in and out of high-speed mode to low power mode, and when you were exiting low power mode and going back to high-speed mode. And again, for those of you, a lot of you guys, this may be second nature, some folks here may not know about this, but basically there's a transition point where each single-ended side transitions to a particular sequence, and then you go to this high-speed mode, and then you have another sequence, and then you transition out of the high-speed mode. So again, this is just kind of important to know, and from a historical perspective, why and how FPGAs are supporting the standard, that's what I'm really trying to tie together here, just to let you know about this particular interface. Okay, so a couple of other points on the interface that you should know about as well, and this is something that's helped the FPGA and the interface itself allow to support multiple cameras. So there's a few things in the interface, and one of those is this VC, or virtual channel. So with one interface, you can actually have multiple virtual channels. And the reason that that is of value is because often, if you want to map multiple cameras with one link, you can use virtual channels to do that. So you can have a dedicated camera on one virtual channel and then additional cameras on another virtual channel, or individual channels per camera. So the interface, the signaling, and the different details of the interface itself allow this and support it. And again, this makes it more welcoming for multiple camera applications. Okay, and by the way, if anyone has any questions, you don't have to wait to the end, just raise your hand. I'm happy to address them or answer them as we go through this. So I just wanted to throw up if you were to talk to a various IP vendor that's here at the DevCon, this is a kind of a picture building block, a block diagram that you'd see. This actually is a differential I/O block. Obviously, you can either transmit or receive, but this does show both. And not only do you have the high-speed SLVS 200 signaling level, but you also have the 1.2 volt CMOS, both the receive and the transmit side. So again, just trying to tie all this together to kind of give you the perspective of what the interface is. And everything that I've been talking about, and the vast majority today of CSI-2 cameras are based on this D5. That's what this high-speed SLVS 200 is, where it transitions to 1.2 volts. Now, those of you may or may not know, I'm just going to have one slide that I want to talk about this, is that the D5 is really dominant, and I do think for quite a number of years we're going to continue to see the D5 used very prevalently, but there is a new standard which is called the C5. And I actually feel fortunate enough to met George from Qualcomm that had invented this. He's actually here. You should introduce yourself to him. He's a really nice guy. And this is actually a 3-wire interface. So very interesting, clever way to, again, allow an embedded clock in the data, where the D5 has its separate clock and data. The C5 embeds it. But again, the point is, this is just for reference. The majority of the cameras today use the D5, and all the applications that I'm talking about, we're going to be focused on the D5. Okay, all right, so I want to just point out what is it and how is it that FPGAs are used with the D5. And so Satwan had mentioned earlier the innovative award that I had won. Myself and another gentleman who actually is here as well, Grant Jennings, who presented earlier. So he and I actually developed a way to allow FPGA differential IOs to interface to cameras and displays that have D5s. So the signaling standard itself is differential, and then you have an option to support single-ended. And there's a number of different ways that this can be done, but this is normally how it's done. Now, there are some newer devices that do have D5, hard D5 blocks in them, but the vast majority are emulating the interface and allowing the signaling standard to be that's supported to work. So again, it's just for reference. These things have been documented, and there's a number of different solutions that are available from a couple of different vendors, including Microsemi. So I don't want to promote anything because I know the MIPI police are out there. This is really intended to be educational and overview, but I just wanted to make sure that folks are aware. Okay, so that's really the primer and the background that I wanted to talk about, and that's what I started with. The next thing I want to shift into is just talk about some of the key building blocks of FPGAs. Some designers that have used mobile components don't know a lot about the FPGA, but there's really 4 key blocks that tend to be used for imaging, video applications, camera applications. And so the I/O gearing, where you have the actual high-speed differential signaling, obviously you need to be able to recover signals at a reasonably high rate. A lot of FPGAs, virtually all of them, have math blocks. These are multiply or accumulate blocks, and these are often used to do and to process images, process the video. So if you want to clean up the images, there's lots of different algorithms that are used, and these DSP blocks are one of the biggest leveraging blocks that are used in the chip. The other one is a memory block. So a lot of FPGAs have internal memory blocks, different sizes. These are used for buffering. You may do line buffers with these, or some more sophisticated tasks. Often you need off-chip memory, but I'll talk about when and when you need it and when you don't. And of course, some FPGAs are system on a chip, have processors, microcontrollers, or microprocessors in them. So again, depending upon how complex the function is, what you're trying to do, you're likely to use some or all of these. Okay, so let's just give you another overview on what are the different standard functions that tend to be used by FPGA. And I kind of bucket them in 4 categories. These are the first 2, and we're kind of going from simpler to more complex. So the first one is just simple bridging, where you have a particular interface and you're bridging it to some other interface. And so, for example, a very common interface is CSI-2 to parallel, or CSI-2 to another standard, as an example. So that's just a simple bridging interface. Doesn't really require significant amounts of complexity. The next function is what I broadly term acceleration. And by acceleration, what I mean is you're receiving the signal, and then you're doing something to it. You may be doing some processing. You may use some of the other earlier blocks that we talked about. And this may or may not require additional memory to store frames for buffering. You may be able to use the internal memory to do that. And so you obviously can mix these, so you could bridge and accelerate in the same device, but just to make it a little simpler and compartmentalized, that's what I was trying to explain on this particular slide. Okay, so what are the other 2 functions, and what is really the focus of what I want to talk about? The next function is processing. So processing is very similar to acceleration. You could think of it as just more complex acceleration functions, where you take the signal in and you're using a lot more of the internal resources to implement an output. Maybe you're outputting more than one bus or interface before you are ultimately performing the function that you want. And then aggregation, and again, this is really where I'm going to focus in on and dive into several applications and explain the use cases and what's being implemented. And here, you're taking multiple inputs, and you could be doing storing or combining and implementing in a variety of different ways. So these aggregation functions tend to use a lot more of the resources of the architecture, and a lot of times these are used because the overall system either doesn't have enough interfaces or for other reasons. And actually, let's talk for one slide on why do you use an FPGA? So what are the reasons? Being in the FPGA business, I sometimes meet customers that haven't used them, and they look at the world and say, hey, I really want it to be glueless. And when I have an FPGA, it means that something's wrong with my system. And the reality is that as the cost of these devices and the features of these technologies get better and better, there's value that they're bringing in other ways. And here's a few of them. So sometimes you're using an application processor or an image signal processor, and you don't have enough inputs, right? You just don't have enough ports, but you want to use multiple cameras. So the engine can process, but you don't have the inputs to get it in. So FPGA can be used for that. Sometimes you just have a limited number of ISP engines on the processor. And so, instead of, having to get an additional one, you could just use an FPGA to do one of the simpler processing and have the AP do the heavy lifting. Sometimes the FPGA does what I call pre-processing. So it implements a function and then passes it on to an application processor. And sometimes, as I've talked to customers, this allows someone to use a lower cost application processor or image signal processor. So instead of spending more money on the processor itself, use the FPGA, do some pre-processing, and I'll show you a couple of examples of this, and then use a lower cost application processor or ISP. Sometimes there's just things that are not available in application processors, whether it's some new standard or some shift of technology. For example, this is not necessarily related, but in automotive, you have a lot more displays in cars than you've ever had. And so, a generation ago, when the AP vendors and GPU vendors were designing their devices, they made assumptions about how many screens people would want. Well, what if you want more screens, right? That's an area where FPGAs can be used. And it's the same for cameras. They make an assumption about how many cameras are really needed, and if there's not enough, FPGAs can be used instead of waiting to redesign the chip and being late to market and so on. And sometimes FPGAs are just used to implement the ISP function instead of an ISP. Some folks are more comfortable coding in Verilog or VHDL, or they have code that they're worried about the security of their IP. They don't want it in software where it can be stolen. So there's a number of factors that also could be there. Okay, so I have a number of applications, and the way the rest of the presentation works is I basically have 2 or 3 slides explaining these various applications. These are all multiple camera applications. CSI-2 applications are obviously the focus of this discussion, and the vast majority of these cameras would be that interface as well. Because an FPGA is flexible, these could be other interfaces, but here what we're really talking about are applications that use 2 cameras for like 3D, a dual camera application in surveillance, an interesting application for HDR with multiple image sensors. That's something that's quite new. 180-degree surveillance applications, 360-degree panorama that you find for surveying and other applications, virtual reality, surround view automotive. I'm not going to go into a lot of detail on that, but we'll talk about how FPGA devices are used. Depth detection applications because of the 2 cameras, a lot of interesting applications in retail and other, and then drones. Okay, so I'm just going to walk through these and kind of give you an overview. Here, what we're showing is 2 CSI-2 image sensors, interface to FPGA. Basically, these are providing the interfaces and then doing the combining and formatting so it can be processed on an AP or an ISP. And, I actually have just been mixing and matching various ISP and AP vendors. I didn't want anyone to get mad at me, so I just kind of used a number of them. So FPGA here actually provides some synchronizing functions and also arranging as well. And so what I mean by that is when you have these 2 images, the ISP that's over here may have the processing power, may or may not have the ability to receive both sensors and combine them. So an FPGA could format the image as like a top and bottom for it so the processor sees it as one, or it can even be side by side. Whatever format that is better for the image processor to work on that and make it look like it's just one camera, that's what the FPGA can do. So when I say sync and format, that's what we're talking about. It's providing that capability. Another application for 2 cameras is for surveillance. So here, again, application where you have multiple CSI inputs, and then you potentially would drive out to an ISP. Of course, you could also go out to a display as well and arrange the different screens. So FPGA can also provide some assistance in doing some leveraging for the image signal processor. So again, maybe you can use a lower cost image processor, image signal processor, as opposed to getting a higher end one. So, this is just an example, but, this is a multiple surveillance camera. Again, you just need one ISP. The ISP has the processing power to handle the 2 cameras combined, but it just may not have the interfaces. So, again, it does the arrangement. It allows the ISP to process the 2 images, but again, the output can still be split. So it's similar to what we talked about with the 3D cameras, but a little bit of a wrinkle in the application. Okay, this application is multiple image sensors. This one would use 3 image sensors and has an FPGA that has a high dynamic range engine in it. And that would be output, either you could do the full processing in the FPGA or you could pass it to an image signal processor. And so what's happening here is that these are the same exact sensors, and one is capturing a short image, one is capturing a medium exposure, and one is capturing a long exposure image. And so what the FPGA does is it actually does tone mapping and other algorithms on those 3 images to give you a recovered image. And so this is an example of what you would expect the output to do. So really interesting here. This is a short exposure, this is a medium exposure, and this is a long exposure. So, you know, it's pretty dark here. It's quite bright in the long exposure. And so, you know, the FPGA takes the 3 of these, it does the tone mapping and processing, definitely needs external memory to do buffering, to run the algorithms across the 3 frames. And then it outputs, you know, a very well-recovered image. And so, you know, in the long exposure, you can see the dog and some of the people, but the sky, the blue, is all washed out here, right? Where it's available here, you can see some of the details in the middle. And so you have an image that's well recovered, and all the darker areas are highlighted and the lighter areas are corrected. So very interesting application, and FPGA is well suited to do this. There's a lot of image sensors that have built-in high dynamic range, but they all have a lot of compromises because, you know, the frame pictures that they take, you know, you can have motion artifact issues and other challenges. So this is another area that's quite interesting for an FPGA. Next application is a 180-degree surveillance camera. So this is actually an application that has up to 5 CSI-2 interfaces, and again, they're combined and stitched together before being either processed, or again, the processing can be in the FPGA itself. So again, this is a function where as you take cameras that are offset, and you can see in this picture here, each one of these cameras are about 45 degrees offset. And so they're also the horizontal, they're off a little bit from the horizontal level. So the FPGA is used to combine those and make sure that the image is perfectly level. So again, the stitching function is one of the things that's done in terms of doing the combining, and you know, the device does comparisons and then is able to, you know, put the full image together. So there's a stitching function. There's also this smoothing function that tends to be done. And of course, the FPGA, if it's large enough and has enough resources, can do the full image processing as well. So very interesting application where multiple products can be used. 360-degree camera. So, you know, it's kind of a similar idea to the 180, just going further. This is not necessarily for functions like in surveillance, but more see this for surveying applications, and also for tying into virtual reality. So you have these cameras set up, you know, they're able to take pictures all around. FPGA is great to do the combining of all of these cameras depending upon how many degrees they're offset. You know, you have the entire stitching and all the rest of the functionality required to smooth and make it all blend together as if it's one image. And you know, I just wanted to show you a couple of outputs you would tend to see from a device like this. So, you know, this is obviously just like a very wide picture, but it's quite panoramic and is a very long and wide view, but it's flattened out. And then there's also this image up here, which is more of the view from the looking up. So again, the images are stitched with the FPGA. The output format, sometimes you can do some correction depending upon the lenses. So if there's fewer cameras and you have a wider fisheye lens, sometimes you need some correction to be done. Again, FPGA can do those functions as well. And again, the image is either processed by the device itself or passed on to a processor to implement the rest of the image processing functions. Okay, surround view. So this is a really, obviously, very popular application in cars. more and more cars are having multiple cameras. I talked to a marketing person at an image sensor company that said in the next generation of automobiles, we're going to have an average of about 12 cameras in a car. So, not only are you going to have surround view, you're going to have cameras for the lane departure warning and for the driving auto drive function, but there's also going to be cameras inside pointed at people, right? So, your insurance company, unfortunately, is going to want to know were you paying attention or you're not. So Big Brother is coming, and there's not a lot we can do, but at least you'll know that if you need to do this design, FPGAs can definitely be used. Here, what we tend to do is interface to these driving chips from various vendors, like FPD3 is a flat link display interface. And again, these tend to be aggregated and then into the FPGA. And again, you can do the combine. They can drive the panel in the automobile as well. Some of the other things that the FPGA often does in the heads-up display is overlay functions. So, in this image, you can see these additional lines. Sometimes they're turn signal lines, but this is, just sort of showing you the bird's eye view put together and then overlaid with directional lines. So a few other applications that I want to talk about. So multiple cameras. When you have two cameras, not only is it for 3D, but two cameras at specific distances apart that are oriented correctly, you can do very accurate depth perception and depth detection. And so there are many applications where using these are just pairs of dual cameras. And again, sometimes you want to synchronize these depending upon what you're trying to process. And again, of course, it depends on the application and what what's being looked at. But this is one application for depth for analytics. So here, this is an application where you have one of the cameras, for example, it's in a store overhead, and you're able to tell how many adults, how many kids, how many dogs or toddlers, what have you, are coming in, because you can tell the height of folks. So hopefully, the algorithm is well tuned so it can kind of figure out, and obviously you could have some blending because there may be some tall youths, but generally speaking, you'd have a good indication not only of how many people are coming through, but what kind of folks are coming through. So there's a depth-based 3D cloud, it's called, picture that's created. And then again, depending upon the height, it's either green is shorter, yellow, again, or red as you're taller. So it's depicted in this image. And then again, the FPGA or processor can tell and share the information on what actually is coming through. Another area for depth detection is in robotics. So there's a lot of assistants, select robot assistants, that's becoming and starting to become very, very popular in a lot of manufacturing and industrial applications. So again, here, you need multiple pairs of depth in a lot of these different robots. And so each of them need to know what the distance is. And one of the benefits of FPGA here is the architecture for an FPGA is in and out. It's a very parallel architecture. It's not like a processor that has to execute instructions, right? So the FPGA is really immune to what I call interrupt latency. When you use a processor, sometimes as you load more and more, and then you start having interrupts, you can have delay in response time. Where an FPGA, it's always going to be in and out, in and processed and out. So that deterministic nature is very valuable in applications where it's safety critical and where harm could come to humans. Just a couple more. I think this is either my second to last or my last couple slides here. So this is an application for drones. So drones have become really popular. Lots of camera makers are very focused in this market. And Some of the higher end drones, what's starting to happen is they're using these dual cameras for depth perception and putting them to really allow the drone to see. So the lower end ones maybe only have one camera that you fly around and a sort of picture is taken or video is taken depending upon where it's pointed to. But you know, if you want a higher end device, you don't want the drone to hit and to run into anything. So this application is an example where you have multiple pairs, left, right, top, bottom, forward, backward. So you could, you know, have 6 pairs of camera on this drone, and this thing would tell you, and again, it creates that 3D cloud image. And so you can see below, hey, there's these wires. So, you know, the drone knows, okay, I'm not going to go much lower because I don't want to run into these wires. So having that view capability all around is key. And what the FPGA really does well here is it basically, it samples and it's looking at all the pairs. And so it knows when it's got something that's maybe orange, kind of getting closer, it can then start streaming more of those camera pairs to the application processor and say, you need to pay more attention here. So it's not just that it's accepting the 2 and implementing some simple functions. You know, it can also throttle bandwidth to the pairs that are most important that have something happening. So I wanted to summarize and explain that the number of multiple camera applications are continuing to grow. These are some interesting leading edge ones, but you know, we see more on a regular basis, and I have no doubt that there's going to be an increased number of multiple camera applications as we move forward. CSI-2 is the standard. It really is. The vast majority of image sensors have this interface. We're going to continue to see a lot more of them. As I mentioned earlier, there are some proprietary standards. Those tend to be in certain targeted vertical markets. But CSI-2 is definitely very popular because, as we mentioned earlier, the cost points and the reliability and the quality. So, you know, FPGAs and more FPGAs will continue to support these interfaces. And the parallel architecture of an FPGA really is great when you do have multiple camera applications. So that's the summary. I wanted to thank you very much, and I guess we have a few minutes or questions. Or if there's
thank you,
else.
Ted.
Thanks.
Any questions for Ted? While you guys thinking, I do have a quick one for you, Ted. So all these, I think, good examples. All these examples are what I consider the uses of MIPI interfaces beyond mobile, which is also a common theme among MIPI and many other forums. So can you put any color for any of these examples as to what's in production, what's still in concept or design stage?
Okay, so the question's really relating to the number of applications and, you know, what would be implemented versus sort of ideas or thoughts in development. So I'd be happy to address that without being too proprietary or without revealing too much information. But so 3D cameras are common and used in many places. Surveillance cameras where you have 2 sensors, that's definitely something that's already out there. Multiple image HDR is pretty new, so this is more in development phase. 180-degree surveillance is out. 360 cameras are out. Surround view automotive, I think most people know there's a lot of different versions, but they continue to enhance them. So there's some simpler ones out and more coming. Depth-based applications, so a lot of these are in development. There's a few that are out, but the mass majority of these are in development. And the drone stuff is in development, and you know, we expect usage shortly.
Thank you.
Yep.
Any other question? Please. Get the microphone.
Yeah, probably similar question. First, thank you. This is a very interesting topic. And also my question is related to the product. So Here it covered most of the topic. I'd like to ask you a question about the traditional camera, so the SLR camera for photographer, right? So do you see anything in those areas, so the product, the MIPI or multi-sensor will be?
For what application were you asking for?
The professional photographer, the camera.
Okay, so DSLR, for example. So, the DSLR vendors, my experience is that they have, there have been very specific image sensors that have been designed for those type of products that are different than the CSI-2. But I do believe that the quality of the interfaces with CSI-2 will get to the point where you will start to see, I think, lower-end DSLRs that will be moving to that.
Okay, one more there.
Thank you for the question.
Hey Ted, just a quick one really. So I think most of these applications need some sort of an ISP pipeline even on the FPGA then.
Yes.
Okay? So, I mean, are there vendors which supply ISP components as well, like as IP?
Yeah, so the question is a lot of these applications, some of them, the image processing would be done in the FPGA, others it would be external. So there are a number of third-party companies that make ISP engines that go into FPGAs. I'd be happy to talk after and we can talk about a few of them, but there's a few that are available, yeah.
Any other question? Thank you, please.
Okay.
Thank you
Thank you
Ted,
very
for your
much.
time.